Hello friends, in our previous video I have given one realization of the positive feedback and the oscillation created from the Barkhausen criteria by one switch concept. So basically what we have done, we replaced this summation block by one switch and we got this diagram. There initially we connected this switch with the XS, that is with the source, and we just applied one full cycle of the small input waveform, and then we got one large output waveform. See here, and it is clear from the diagram that the amplifier the basic amplifier whose gain is A is basically one non-inverting amplifier, because the input signal and the output signal are in same phase. You know these basic concepts. Now what we do in the second step, we open this switch and we connect this switch in between the XF, that means in between the output of the feedback network and the input of the basic amplifier block. That means basically what we do in the next stage, we remove the switch from here and we connect the switch here. Okay, you can check my previous video, there I have mentioned this concept. Okay, and then what happens basically, see here we have removed the switch from the input and we have connected with the feedback network, and as I have shown in my previous video that if A beta equal to 1, then the output of the feedback network, that is this signal, will be same as input signal. That is, if A beta equal to 1, then after one full loop rotation, that is after one full loop rotation, the X of F will be exactly equal to X of S, that is first input cycle whatever we have given to start the oscillation. Now this will be the input of the basic amplifier block, and this will generate the next full cycle of the output waveform. Okay, see I have drawn here the same diagram, that is the red full cycle, that is from this to this cycle was generated by the input signal whatever we have given from X of S. Now the second output cycle, third output cycle, fourth output cycle, and so on, it will generate due to the X of F, because X of F is exactly equal to X input whatever we have given in the first step. Okay, in this way oscillation is sustained. This thing I have already mentioned in my previous video. Now one very important question arises, that to start the oscillation we had to give one, sorry, I will remove this. Yes, now see, to start the oscillation we must have to give one small input signal of one full cycle. How this small input signal is generated in the circuit? Basically in the practical network we never give such a input signal for one full cycle. For time period T, for one full cycle we never provide the basic amplifier an input. So how in practical this one cycle or the starting voltage generates? This is the question. The starting voltage is generated from the noise created from the electronic components which are used to make the basic amplifier block or the feedback network. Okay, I will discuss in detail. See here, we just considered one random noise. See here, this is the diagram of one random noise. Here in y-axis random noise is plotted and in x-axis time t is there. Clear? Now how we can realize this noise? Basically what I want to say, I will prove that in thermal noise there are many frequencies. Okay, not single frequency. So that for example purpose I have just chosen one random noise like this type of waveform. So basically how to generate this type of random noise? So first let us assume one pure sinusoid waveform A naught sine omega naught t with angular frequency omega naught, which is equal to 2 pi f naught. F naught is the frequency of the pure sinusoid, amplitude is A naught, and this is the diagram. Now this pure sinusoid is not this random noise. Okay, so what we do, we just superimpose one another sinusoid like this way. Okay, we just put another sinusoid on A naught sine omega naught t like this way, and we get this waveform. See here, I have drawn the complete another black color sinusoid waveform on the red sinusoid waveform. So basically now this signal becomes A naught sine omega naught t plus A1 sine omega 1 t, where A1 sine omega 1 t is basically the black waveform. So basically now we can say that we got like this kind of waveform. See carefully, if you combine the black sinusoid and red sinusoid, we will get this type of distorted noise kind shape, random noise. Okay, some more frequencies can be added like A2 sine omega 2t, A3 sine omega 3t, like, and so on, and then by adding all these we can get this random noise. Okay, so basically what I want to say, that in random noise multiple frequencies present. Okay, see here only from this discussion only you can say here omega naught is one frequency, omega 1 is another frequency. So basically this signal is composed of two different frequencies. So what we do, instead of representing this signal in such a way, we represent in frequency domain in such a way. In the y-axis x of t is plotted, and in the x-axis omega or angular frequency is plotted. Then we can represent this signal as this one, that at omega naught frequency the amplitude of the sinusoid is A naught, and at omega 1 frequency the amplitude of the sinusoid waveform is A1. So this is very easy to visualize this signal instead of this expression. Okay, instead of this expression, if I say you in this way, that at omega naught frequency A naught, that means A naught sine omega naught t, and at omega 1 frequency A1, that means A1 sine omega 1 t. So this is very easy to visualize. So what we do in signal and system, you will study this, that instead of representing a signal, random signal in time domain, we like to represent in the signal in frequency domain, because scientist Fourier said that any signal could be made up by adding together a series of sine waves with appropriate amplitude and phase. Like here I have given one example. So what I mean to say, that one noise which is random in nature, like you just consider thermal noise. So any noise like thermal noise has multiple frequencies. Okay, up to this I hope the concept is clear. So what I told, that the starting voltage is provided by the noise, I told already in my previous video, which is produced due to random motion of electrons in resistors used in circuit. Okay, you know how noise is generated. If you don't know about noise, obviously you will study in detail in your next semester course, that is analog communication system. There one full module on noise is there. Okay, there you will study in detail. I am not going in that much detail. And this also we have got the idea that the noise voltage contains almost all the sinusoidal frequencies. Like in my previous slide I have shown that the noise signal contained omega naught, omega 1, omega 2 and so on. So now the question is how the oscillation is created from this type of all when in a particular voltage different frequencies are present, then how it can generate a output voltage with a particular frequency. That I will discuss now. See, this is the basic diagram of positive feedback. As you know, the basic concept is V output by Vs, that is overall loop gain, is equal to A by 1 minus A beta, and if somehow we can manage to make A beta equal to 1, then in that case V output by Vs obviously equal to infinity, and that means Vs equal to 0. That means without applying any input we can get, without applying any input we can get the output waveform. Okay, now see what I told, that basically here in the input we apply one noise. Basically we do not apply in circuit by default, it is applied different like distorted shape noise is applied, and it contains various frequencies omega naught, omega 1, omega 2 and so on, but the output will be only one frequency with very high amplitude and particular frequency omega naught or omega 1 or omega 2. How this is generated? See, that's why I have written here selective network. What the selective network means, that I will discuss. So before that, basic amplifier block gain is A, which is function of frequency, because you know that for suppose for C amplifier the gain versus frequency graph goes like this. In the y-axis gain is plotted and the x-axis frequency is plotted, then we can get this kind of graph, and this is called midband gain. So the basic amplifier block gain is frequency dependent, and one of the important characteristics in positive feedback to make oscillator is the selective network is also frequency dependent. That means the gain of this selective network is frequency dependent. That means we make the selective network with inductor, capacitor, etc. When I will discuss the practical selective network, you can clearly understand. I will discuss in my next videos. So selective network beta is a frequency dependent, so I have denoted by beta f. Okay, you can clearly realize this by one concept, that in when I taught you the negative feedback, then I told that the beta is basically attenuator, and most of the case for negative feedback it is purely resistive, so that there is no phase shift. But suppose in positive feedback, if we apply inverting amplifier, then obviously 180 degree phase shift will occur here. So to make total in the total whole loop, to make 360 degree phase shift, the beta network also should provide 180 degree phase shift, and we cannot provide phase shift by resistive network. So obviously we have to apply inductor and capacitor in the selective network. From that also you can get an interpretation or an intuitive idea that the selective network for positive feedback is basically frequency dependent, because it is made up of inductor and capacitor. So gain is frequency dependent. So as the A and beta are frequency dependent, what will happen? This A beta will be equal to 1 will not satisfy for any frequencies. For a random frequency omega naught, omega 1, omega 2, it will not satisfy. For a particular frequency, A beta will be equal to 1. And for that frequency, when A beta equal to 1, then V output by Vs equal to infinite, that is overall gain theoretically will be infinite, or in practical we can say that overall gain will be very high. So although the input noise which starts the oscillation has various frequencies, but there is one particular frequency in that noise. If you derive the Fourier expression, then you can get many frequencies which is there in the noise. You can get one particular frequency from that, for which A into beta will be 1, and in that case the overall gain of the network will become very high, and from this small noise voltage we can get large output voltage. Okay, small noise voltage means noise voltage is how much? 2 microvolt, 2 millivolt maximum, or 2 nanovolt, like that. So we apply, this is not proper output waveform, but just you consider this. This is sinusoid oscillation. Just we apply some distorted noise shape, and from there, due to frequency selective network, one particular frequency will be selected, for which the A beta gain is equal to 1, and in that case the overall gain of the circuit becomes very high, theoretically infinite, practically very high, and so that at that frequency component we can get the oscillation. Now you just got the whole idea that how oscillation is created from the noise. Okay, so from noise, from various frequency, one particular frequency is chosen by the frequency selective network. It is amplified huge amount. Okay, because at when A beta equal to 1, the practical gain of the overall gain of the network is very high. So output oscillation we will get from very small input noise. This is all for this video. Thank you.